As I said, perceptron will find one possible classifier, but maybe this classifier is very close to some of the points, is not necessarily on the line more equidistant between the positive and the negative. Another problem is that yes, they are linear classifiers, and in general, linear classifiers generalize relatively well, and we can also use the epoch parameter as a form of regularization, as a form to decide how deep going in our training. But still, the problem is that this clearly is not good. If we use perceptron with this dataset, we may well end up with classifiers of this type that is very dependent on noisy data and clearly doesn't generalize well with the nature of the data that we have. So I introduce here support vector machines, SVM, and we will not develop SVM further in this course except in these small discussions. And SVM are still linear classifiers, but they have the characteristics that try to maximize the boundary with the classification data. So we are no longer like here possibly very close to the data, but they try to have margins on both sides and maximize the minimum margin so that they will be somewhere here like at the center of the two. To do that, we enter somehow the realm of optimizations, because this passage here is achieved by maximizing the margin, and this is doing by employing a gradient-based approach, and this gradient-based approach we'll see when we'll discuss neural network, because it's basically the same. So it's no longer indifferent one classifier that separates the data from another, but really here with SVM we should find the classifier that is more far away from the dataset on both the directions. But there is another characteristic of SVM that is very important and make it really outstanding compared with perceptron for a linear classifier, and it is that this optimization here can be somehow adjusted with one parameter that takes the form of a regularization parameter that tries to optimize not only the distance of the points that are more close to the classifier, but all the points. So to consider not only this point here that in the terminology are the support vectors, and this is the why it's called the support vector machine, the points that are closer to the boundary and decide exactly the slope of the classifiers, but to consider also all the other points. And when you consider also the other points, try to minimizing the errors, but at the same time keeping the biggest, the largest boundary that you can, you end up to find using the algorithm of support vector machine, or using this optimization corrected with this parameter of regularization, a classifiers that like this one, but it may make some errors, 2 errors in this case with the training set that is provided, but do generalize much better with the specific nature of the problem that we have. And the way we'll find this optimal regularization hyperparameter is indeed using the cross validation or the normal validations that we saw here. We conclude this first segment more theoretical on one note on using linear classifiers to perform non-linear classification, or using linear to make non-linear regression. So sometimes the relation between the x and y is not linear in its nature, and even employing the best linear classifiers, we would end up to making considerable errors. So we have a good news, is that we can easily still use linear classifiers to do nonlinear classification by just engineering our data. And here is a very simple example. So here is our original dataset in 1 dimensions, and this dataset is clearly cannot be linearly separable in 1 dimension. There is no way that I can put one classifiers that here will be represented by a dot and correctly classify all the points. However, we can introduce a new dimensions, for example, making the square of the first dimension. And when we make the square of the dimensions, we end up here, and at this point we can easily find a linear classifiers in 2 dimensions that separate our data, okay? So the good news is that we can engineer our data to add nonlinear features based on our original features and use a linear classifiers on that. The bad news is that this kind of engineerization, sorry, I don't know if the word exists, this sort of engineering our data is something that we do based on our knowledge of our expert knowledge of the data. Is not something that is learned by the algorithm, okay? It's just we do this one and then we apply our linear algorithm. And this is the key difference between linear algorithms that are used together with feature transformations and which are the more modern kind of nonlinear algorithm. And this nonlinearity in the data is itself learned from the data, like in tree-based approach and in neural networks. And so this is why these are much more powerful, because if the relation is linear, we will end up some classifiers that somehow remain linear. If the nature is non-linear, is the classifier or the algorithm to find to operate a regressions that will look and somehow by itself find this non-linearity. So here is all is overall presentation of the main concept of machine learning algorithms, and we can now go on and implement in Julia the perceptron algorithm and perform a little bit of cross validation.